Hey everybody, welcome back. This is Chem 309 and we're starting chapter 5 today, which is all about molecules and compounds. So chapter 5 is going to be divided into 3 parts. The first part is on compounds and constant composition, chemical formulas, how we represent compounds, a molecular view of elements and compounds, and writing formulas for ionic compounds. Then in part 2, we're going to get into what's called nomenclature. That's how we name compounds and go between a name and a formula, or a formula back to a name. So we're going to learn how to name and write formulas for ionic compounds, and we're going to learn how to name and write formulas for molecular compounds in part 2. Then in part 3, we're going to continue with nomenclature. We're going to learn how to name acids, which are a type of molecular compound. And then we're going to summarize all the nomenclature we've learned so far and work through quite a few example problems. And then the last part of the chapter is on formula mass, which is the mass of a molecule or one formula unit of a compound. All right, let's get started. We'll start with chemical compounds and constant composition. Our goals in this section are to define a chemical compound and to talk about and define the law of constant composition. So chemical compounds are a substance composed of 2 or more elements that are chemically combined in fixed proportions. So what this means that you need to have for a chemical compound is you have to have a substance that has 2 or more different elements that are chemically bonded together. If you have a substance where it's all the same element, then we're going to learn that that's later defined as an element. It won't be called a compound. So to have a compound, you have to have 2 or more different elements, atoms of 2 different elements or more. The elements in a compound are also always present in the same proportions for a given or specific compound. What this means is that, for example, water, H2O, always contains 2 hydrogen atoms and 1 oxygen atom, by definition. If the proportions of the atoms were changed, let's say that we suddenly had H2O2, it would no longer be water, because the proportions of our hydrogens and oxygens has changed. For this compound to be called water, it needs to have 2 hydrogen atoms, H2, for every 1 oxygen atom. In fact, H2O2 isn't water, it's hydrogen peroxide. So vastly different compounds. You can drink water and be totally fine. If you drink hydrogen peroxide, you get really sick. So the proportions of the atoms in a compound is what defines the identity of that compound. Chemical compounds can be chemically decomposed. That means they can be broken down into simpler substances through a chemical reaction or a chemical change. So for example, we have a simple compound here, we'll just call it XY. If it undergoes a chemical reaction in which the compound XY breaks into the elements, that's a chemical change. The bond between X and Y was broken to produce the simple elements X and Y. Here's a real life example. Hydrogen peroxide, H2O2, can be chemically decomposed into oxygen and water. So we're starting out with a more complex substance, a compound, and it gets broken down into an element, oxygen, plus another compound, water, which is simpler than hydrogen peroxide. We had 2 hydrogens for every 2 oxygens there, and now we have H2O, so it got simpler. So that's what we mean by chemical compounds can be chemically decomposed or broken down into simpler substances. And if we keep doing this, eventually we would end up getting just all the elements, oxygen and hydrogen. Just a note on the practical application of this. If any of you have hydrogen peroxide in your medicine cabinets, you might use it to disinfect wounds. Hydrogen peroxide naturally undergoes this decomposition over time. This happens naturally over time. So if you have really old hydrogen peroxide in your medicine cabinet, it may have already chemically decomposed over time into oxygen, which would just leave the hydrogen peroxide as oxygen gas, and water. So I've had some instances where I have some really old hydrogen peroxide in the medicine cabinet. I pour it on a cut. If it's fresh, it usually stings a bit. That's it forming gas to help disinfect your wounds. But if it's really old and it doesn't sting anymore, it might be because it's already decomposed and all you're doing is really pouring water on your wound. So go check those expiration dates because that will happen over time slowly as it sits in your medicine cabinet. So the properties of a compound are in general different from the properties of the elements that compose it. So let's look at sodium chloride as our first example. Sodium chloride is made from sodium and chlorine. Its chemical formula is NaCl. And this is just regular table salt. But the elements that compose it are very different in their properties from the resulting chemical compound that's formed when they bond together. So elemental sodium, just solid sodium, is an extremely reactive metal. It dulls almost instantly upon exposure to air, and it reacts very, very violently with water, creating a bunch of heat and hydrogen gas, which causes the hydrogen gas to flame up and explode. And then elemental chlorine, the other element in sodium chloride, is a yellow gas with a pungent odor, and it's highly reactive and highly poisonous. So each of these elements, Na and Cl, you wouldn't want to come into contact with. But when they chemically combine to make sodium chloride, the compound, this is table salt, and we eat this in almost all of our foods. Sodium is an essential ion. It circulates in our blood. It helps maintain homeostasis for our cells. So the elements that make up compounds are going to have very different properties than the compound they form when they chemically bond together. Another example is sucrose. Sucrose is just ordinary table sugar. The sucrose molecule, shown here, is made up of carbon atoms, hydrogen atoms, and oxygen atoms. Its formula is C12H22O11. So sucrose has very different properties than the element is made up of. Right, here's carbon, graphite, solid carbon, oxygen gas, highly flammable, and hydrogen gas, also highly flammable. So again, the properties of a compound are very different from the properties of the elements that compose it, because when things chemically combine, it's changing their electron configurations, they're getting to a more stable state, and so the properties are going to change. In compounds, the elements combine in these fixed, definite proportions. This is different than a mixture. So in mixtures, say a balloon filled with oxygen and hydrogen, the ratio between oxygen and hydrogen can change in that balloon, depending on how much oxygen gas you pump in and how much hydrogen gas you pump in. Versus in a chemical compound, say a balloon filled with water, H2O, the composition of water is always the same. Water always has 2 hydrogen atoms and 1 oxygen atom. And so that's what we mean when we say that compounds have fixed, definite proportions. If we change the proportions of hydrogens to oxygens here, it would change the identity of this compound. So this brings us to what's called the law of constant composition. This was formally stated in the early 1800s by Joseph Proust. He stated the idea that elements combine in fixed proportions to form compounds. And so the law of constant composition is that all samples of a given compound have the same proportions of their constituent elements. This is just to say that anytime we have, say again, water, H2O, is always 2 hydrogen atoms plus 1 oxygen atom. Another example, glucose. This is an important sugar or carbohydrate in metabolism and energy production. It's always C6H12O6. Always. Another example, sodium chloride. It's always 1 sodium plus 1 Cl. If the proportions changed, it would no longer be that same compound. So this means if you decompose or break down a compound, the ratios of the masses of those individual elements is always going to be the same for the same compound, because the same compounds always have the same proportions of atoms in them. So for example, water has 2 hydrogen atoms and 1 oxygen atom. So if we break apart 18 grams of water, we decompose 18 grams of water, we'd end up getting 16 grams of oxygen and 2 grams of hydrogen. If we take the ratio of this, you always put the larger mass on top. So 16 grams of oxygen to 2 grams of hydrogen, 16 over 2 equals 8. So we'd say the mass ratio for water, H2O, of oxygen to hydrogen is 8.0 or 8 to 1. That means for every 8 grams of oxygen we have 1 gram of hydrogen. And this is because the proportion of the atoms in this molecule is always the same. And atoms have mass, right? Atoms are matter, matter has mass and volume. So because we always have 2 oxygen atoms, 1 oxygen atom for every 1 hydrogen atom, the ratio of those atoms is always the same for the same molecule, which means the ratios of the masses of those atoms is always the same as well for the same molecule. If you take note here, if we add up the masses of each of the elements in this compound in H2O, we get the total mass that we started with. 16 grams of oxygen plus 2 grams of water equals 18 grams of that total sample we started with. So this law of constant composition can be useful in figuring out how much of an element you have present in a compound. If you're able to decompose the compound, you know the mass ratio and you can measure the mass of one of the elements, you can always figure out the mass of the other element using this mass ratio formula. So let's do an example of that. So ammonia, NH3, has a mass ratio of 4.7 grams of nitrogen for every 1 gram of hydrogen. So if we took a sample of ammonia and we decomposed it and we obtained 5.6 grams of hydrogen, how many grams of nitrogen must have been in that sample? And can we figure out the total sample mass? So we're going to use law of constant composition to solve a problem like this. Law of constant composition says the mass ratio for 2 elements in a compound is always going to be constant for that compound. You take your grams of element 1, and I always put the heavier 1 on top because I like getting mass ratios that are whole numbers that are positive. And I put the mass of the lighter 1 on bottom. So we were told the mass ratio is 4.7 to 1. So our mass ratio is 4.7. And then we were told that when we decomposed our sample, we don't know how much sample we have, but when we decomposed it, we ended up getting 5.6 grams of hydrogen. So we have our grams of nitrogen and 5.6 grams of hydrogen that we obtained when we decomposed our sample. And the mass of the nitrogen divided by the mass of the hydrogen, the ratio of those two is always going to equal 4.7 for ammonia. So using this formula, we can solve for the grams of nitrogen. How many grams of nitrogen must have been in that sample to obtain a mass ratio of 4.7? Because no matter how little or how much ammonia we have, the mass ratio is always going to be 4.7 because the chemical formula is going to always be the same for ammonia. So let me grab my calculator here and we'll figure this out. To solve for grams of ammonia, you need to get that by itself on one side of the equation. So we're going to multiply both sides by 5.6 grams of hydrogen to cancel that out. So we get 4.7 times 5.6 equals our grams of nitrogen. And I get 26.32 grams of nitrogen. And if we check our sig figs, like we always have to do anytime we're doing calculations, we had 2 sig figs in our mass ratio. We had 2 sig figs on our mass of hydrogen, so we should end up with 2 sig figs on our grams of nitrogen. So if we wanted to check to make sure this was correct, when we take our grams of nitrogen, 26 grams, and we divide it by our grams of hydrogen, 5.6, we should get about 4.7 if we did this correctly. So I'm going to check. because I like to know I did it right. I got pretty close. I got 4.64. It's a little off because of this rounding that we did, but close enough to say we did the math correctly. We didn't flip our ratio or something like that. So now that we know how much nitrogen we must have had in our sample, we had 26 grams of nitrogen, and we had 5.6 grams of hydrogen. So our total sample mass is going to be the masses of both of those elements added up, since those are the only two elements in our compound. So our total sample mass is going to be 5.6 grams of hydrogen plus 26 grams of nitrogen. Yields 31.6 grams. And if we check our sig figs, 5.6 ends in the tenths place and 26 ends in the ones. So we need to round this to the ones place. So we started with 32 grams of ammonia. So if you decomposed 32 grams of ammonia, you broke it back up into nitrogen and hydrogen chemically, you'd end up with 26 grams of nitrogen and 5.6 grams of hydrogen. And that's what the law of constant composition says, because the ratio of the atoms is always going to be the same in ammonia. That means the ratio of the masses of those atoms is also always going to be the same. So we're next going to talk about chemical formulas, which is how we represent compounds. I'll see you then. Thank you.